everyone, I am Narendra. In the last video, I have given some introduction to physics of semiconductor devices. In this video, we will try to learn about energy bands in semiconductors. So if you take any semiconductor based device like diodes or transistors, to understand these devices, you should know the energy bands of semiconductors. Once you know the energy band diagram, you can easily understand the performance of these devices. So what are these energy bands? How these bands are formed? In this video, we will try to understand briefly about these energy bands. So let us consider a simple single atomic system, right? Hydrogen atom, 1s1. You know the Bohr model of atom, right? There is a nucleus and there is an electron in the orbit. Okay, this is bound to the nucleus. So let us take two hydrogen atoms. So initially, these two hydrogen atoms are far apart. That means there is no interaction between them. So you know the electron is a subatomic particle. It behaves like a wave. So when these two atoms are brought together to form an interacting system, so these electrons are try to interact each other. Their wave function overlap here, right? So in this interacting system, so according to Pauli exclusion principle, no two electrons have same quantum number. So initially there is a single energy state, so that are discrete energy states, right? So when you make a interacting system, so these energy states will split to two energy states because no two electrons have a same quantum number. If you put n number of atoms together to form a solid, so these energy levels split to form a band of energy states. Because of the splitting, so the band of energy states will be formed in this solid. Okay, so within this band, these energy states are also discrete in nature, right? So let us understand more clearly if you take a system with more number of electrons, right? So let us take a silicon atom. So you know the atomic number is 14, right? So the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p2, right? So here you take a Bohr atomic model way, right? So there is a nucleus, right? So there is a 1s, then 2s and 2p, then 3s and 3p, right? So these two electrons, these two 1s2 and 2s2, 2p6. So these electrons are more close to the nucleus and these are more bound to the nucleus compared to the electrons in the 3s and 3p, right? So these electrons are core electrons and these electrons are valency electrons, right? So generally if you combine atoms initially, so these valency electrons are try to interact first. So then if the atoms are more closer and closer, then their core electrons will try to interact, right? So let's see how the bands are formed, right? So let's see how the bands are formed here. So let us plot electron energy as a function of interatomic spacing, right? So here we are talking about crystalline materials where the atoms are arranged in a periodic way with periodicity or lattice constant is A0, right? So if you take another form of materials like amorphous, where this order is very short, so the short range order here. So atoms are arranged in a random way, but in a crystalline materials, the atoms are arranged in a periodic way. So here we are discussing about these. Okay, so when these atoms are brought together to form a interacting system, so that gives the splitting of energy levels to form a band, right? So here we'll see. So when these atoms are far apart, so all are discrete energy levels, right? 1s, 2s, 2p, 3s, and 3p, right? 3s and 3p. So when you put atoms together, okay, so these 3s and 3p first interact each other, okay? So the electrons in the 3s and 3p interact each other. So then there's a splitting of energy bands, right? There's a splitting of energy bands, okay? At some point, so these bands are merged together to form a single band, right? So this 3s, if you take a n number of atoms, right? So there are 2n states in the 3s orbital, 2n states, and there are 2n electrons, right? Here you can see the 2n electrons, right? So in case of 3p, there are 6n states, but in this only 2n electrons are there. 2n electrons are there. 2n electrons are there, right? Okay, only 2n electrons are there. So here, so when these bands are merged, so here you can see there are filled states with these 4n electrons. So these are filled states, right, with the 4n electrons. And these are unfilled states. So these are unfilled states, okay, so that are 4n states, and here 4n states, total 8n states, okay? So in this 8n states, okay, so these here the bands are merged and there are 8n states, 4n states are filled and 4n states are unfilled, right? So when these atoms are more closer and more closer, so these 2p and 1s are also try to interact. The electrons in the 1s, 2s and 2p also try to interact and then form a band of energy states, okay? So in this way the bands are formed, okay? So at an equilibrium position, or you can see that if the atoms are more closer and more closer, so these filled and unfilled states will separate it, okay? So when the atoms are more closer and more closer, so these filled and unfilled states are separated, okay? These are all filled and these are unfilled, okay? So at equilibrium, that means there is no attraction or repulsion between the atom. So at equilibrium position, right, A naught, this is the atomic spacing, right? So these are atomic spacing in a crystal, So at equilibrium position, okay, so there is a gap between the filled and unfilled states, so this gap is called energy band gap, or forbidden gap, okay? So in this way the energy bands are formed in solids like semiconductor. So here I took example of semiconductor, right? So in this way the energy bands are formed with a energy band gap, right? So I hope you understand something about energy bands and energy band gap in semiconductors. So next time we'll see with the other discussion on these energy bands, okay?
To see more videos like this, and please consider subscribing.